All right, we conclude our study of oscillations looking at devices called pendulums. A pendulum is a point mass suspended at one end of an ideal massless string or rod, with the other end held at a frictionless pivot but free to swing back and forth. This is what's called a simple pendulum. If the mass is not point-like, the system is called a physical pendulum. We won't be analyzing those in AP1. We can say our setup here where we have our string hanging, we pull it over, and we say there's some angle theta, and string length L, and some arc length S that we've moved it. And we define some coordinate systems so that they're positive on one side and negative on the other. So let's consider the dynamics of this system. The bob moves back and forth along the circular arc, and only the tangential component of gravity acts in that direction, so that the net force in the tangential direction is mg sine theta. So remember, we've got our weight variable here, and we want this part, which is clearly the opposite side, so we get the weight times sine theta. And the weight, of course, is mg. Now we're going to use a trick from calculus, which is that if theta is measured in radians and is quote-unquote small, then sine of theta is about theta. This tells us that F net in the tangent direction is minus mg theta. With that restriction in place, we see the pendulum motion has a linear restoring force, so it's mathematically identical to simple harmonic motion. How small is small? Well, these two things, here's a graph of sine of theta and a graph of 0.95. So we see that sine of theta is within they agree to within about 5%, as long as theta is about 0.55 radians or smaller. But 0.55 radians is about 31 degrees, which is about a third of the full way towards a full right angle. And so it's not really that small. It's a third of the way you could go. If you decide that 5% is too generous and you agree on only 1%, that's what you have to stay within 1%, then the maximum angle turns out to be 0.245 radians, which is still 14 degrees. It's very noticeable, a 15-degree angle. So small is not very small here. We're not talking about infinitesimal or even tiny. We're talking about real, if smallish, angles. Because the math is the same, we can reuse all the results from the spring system analysis, but we notice that the spring constant is this k, this quote-unquote fake k, would be the weight over the length. And that's just coming from that formula for the tangent force, which is that the tangent force, right, the net tangent force was minus mg over L times theta, and this is analogous to minus kx. So our spring constant, our quote-unquote spring constant, would be mg over L. Something weird happens. Because k includes m, because this fake k includes the mass itself, the mass drops out of the period relation. We say that we have, for a spring, it was t is 2 pi times root m over the spring constant. So 2 pi root m over mg over L. And then we flip and multiply, and we get 2 pi ml over mg. And so we end up with the very important and relatively simple result that the period is 2 pi, again, root L over g. Couple of things. Let's check if that makes any kind of sense. Sort of. The longer the string, the slower the pendulum is going to go back and forth, because any given angle is a much bigger displacement. So that makes sense. It takes longer to go back and forth. And then, although we can't vary gravity on Earth, we could imagine if we pulled down harder that the pendulum bob would swing through faster and we get a lower t. So this at least makes sense. And then the really important thing to note here is that the amplitude still isn't relevant as long as the angle is small. So that's a little weird. It doesn't depend on the angle as long as the angle doesn't get too huge. So if our initial angle, which is the largest it's ever going to get, is sort of, half a radian or less, then it's going to stay half a radian or less and we'll be okay. And then it doesn't really matter which of those angles we picked. All right, the dependence of the period on the length, but not on the mass or the amplitude, is historically very significant. It allowed constructions of the first replicable, reliable mechanical clocks. It's possible to define a standard unit of time simply by agreeing on a set length, which is easily done. It's simply not hard to transport a pre-measured length of string, or at least to agree on what length of things are, and then cut your own string to the appropriate length. Although precision clockwork quickly left behind the simple pendulum, this introduction of a standard objective time underlies much of the scientific revolution and the industrial revolution that it spawned. In a very real sense, the modern peoples experience time in a way vastly different than the early peoples because of pendulum clocks. Here we see a cute illustration of how the period depends on time with what's called a pendulum wave setup. It's kind of worth watching. All of these pendulums are started at the same angle at the same time, but have different lengths and therefore different periods. They're double connected for stability, but it doesn't change the analysis in any way. And because the period is different, we get this divergence that gives us this weird little wave-like effect. But of course, everything's periodic, so it has to go back to where it was before. And then eventually mix in again. What we're also seeing is that for pendula of different frequencies, they can mix in interesting and weird ways that we would talk about a little bit later in the wave unit. And then eventually they will get back to being the same thing, and then they'll swing out. You can see that there's a little bit of friction and a little bit of loss, and it's not quite the right lengths because this one up here fell out of phase. Alright, a pendulum clock is made with a metal rod. It keeps perfect time at a temperature of 20 degrees Celsius. At a higher temperature, the metal rod lengthens. How will this change the clock's timekeeping? Because the rod is longer than it was supposed to be, the period is longer than we originally had. Assume we have this clock and a existing perfect clock synchronized at noon. When 1 hour on the perfect clock has passed, it hasn't yet been a full hour on the actual clock because it's repeated fewer times because the period is longer. So the actual clock is running slow, which is answer C. All right, a ball on a massless rigid rod oscillates as a simple pendulum with a period of 2 seconds. If the ball were replaced with another ball having twice the mass, what would happen to the period? So we look at our formula and we have that the period is 2 pi root L over G, and we see that the mass is not in that, so having twice the mass doesn't do anything. We still have period 2 seconds. Need to be careful because, of course, if you just do this blindly, you're like, oh wait, 2 pi root m over k, but that's for a spring system. And remember that the spring constant in this case is also dependent on the mass in such a way that the mass drops out. On planet X, a ball on a massless rigid rod oscillates as a simple pendulum with a period of 2 seconds. If the pendulum is taken to the moon of planet X with a free fall acceleration g is half as big, what happens to the period? So the period here, as we said just a moment ago, is this. Let's call that the initial one. And then our new period is going to be 2 pi root L over the new g. But that's 2 pi root L over 1/2 g naught. So 2 pi root 2L over g naught, which is root 2 times 2 pi root L over g naught, or root 2 as large. Since we start at 2 seconds and the root of 2 is 1.4, we get 2.8 seconds. A series of pendulums with different length strings and different masses are shown below. Each pendulum is pulled to the side by the same small angle. The pendulums are released and they begin to swing from side to side. Which of the pendulums oscillates with the highest frequency? So we start off by saying the frequency is 1 over the period. So high frequency is low period. And the period is 2 pi root L over G. So the low period comes from the least distance. And we get, it must be A. Also, of course, it's multiple choice, and since it only depends on the lengths, and 3 of the lengths are the same, it can't be any of them. But that's just a trick of the particular way the question was phrased. A grandfather clock is designed so that one swing of the pendulum in either direction takes 1 second. What is the length of the pendulum? So here our period is 2 seconds, because they say out is 1 second and then back to the other side is 1 second. But the period is also 2 pi root L over G. So we have L is, let's see, square both sides. All right, we go here. T squared is 2 pi quantity squared L over G. So L is T squared over 2 pi quantity squared times G, which turns out to be about 0.993 meters, which is why grandfather clocks tend to be about a meter tall. Well, the strings in them.